chapter 16, number 95. How many milliliters of 1.50 molar sodium hydroxide solution must react with aluminum to yield 2.00 liters of hydrogen measured at 22 degrees C, 789 torr by the reaction here. Assuming the complete conversion of reactants to products. So when you look at this particular reaction, it kind of looks like what? It looks like a single replacement reaction, doesn't it? But it doesn't fit the single replacement form here. This is a bit different reaction here. There's definitely a redox reaction, but it's a combination of a redox reaction. Well, it looks like a Lewis acid-base reaction. And sometimes what we see that happens, like a net. They'll show the net, but we can break it down into simpler steps here. But what we have here is a mix of solid. I don't know why your book doesn't do this, but I wish they did this. It's good to get in the habit of writing things out, particularly the states. So aluminum is a solid, liquid, gas, or AQ. So solid. Aluminum's a solid. And sodium hydroxide, solid, liquid, gas, or AQ. AQ. We have 2 aluminum, 6 sodium hydroxide. Yields. Okay, now that species there, would you put that at? Well, we know what the cation's called. It's the sodium cation. The anion is a bit tricky though. The anion would be like maybe an aluminate or aluminite. No, that's aluminate is usually a little cool. But anyway. We don't need to name that. We're going to have 2 Na3. Sodium's a +1, so this AlO3 must be a net -3 charge here. That sodium salts are soluble, so that's going to be soluble. And then H2 is a gas. All right, so they give us the amount of H2. How much H2 formed in this particular reaction? We end up with how many liters of H2? Yeah, we end up with 2.00 liters of H2 gas. Well, how much is that? Well, how many moles is that? The number of moles depends on the pressure. You know, if you have high pressure gas, you got a lot of moles in there. Low pressure gas, not that many moles. So it depends on how many moles you compress in that 2 liters. Well, we have two ways to figure out the moles. You know, for gases, we can go straight from liters to moles. There are 2 ways to go. One way is we could use the ideal gas law. N is equal to PV over RT. Or 2, we could use the molar volume. The molar volume, this one we don't have memorized because this one, the molar volume could be at 22 degrees C at 789 torr. So what's your preference? Should we use the ideal gas law to convert it to moles, or should we use the molar volume? What is your preference? The advantage to doing it using molar volume is we can string it along into one-dimensional analysis equation. The advantage of using the ideal gas law is just to get more practice with the ideal gas law. So what's your preference? Well, probably no preference means, you know, the more of these problems you do, then you'll start to develop a preference, or maybe you still won't develop a preference, but it depends on how many of these you do. So which one are you more comfortable with? Ideal gas law or molar volume? neither. Maybe you haven't done any of them. Yeah. Well, if you have no preference, then I'll just use molar volume. Molar volume is equal to RT over P. We'll just calculate it. R is 0.08206 liters per milliliter.
Let's see.
Per mole Kelvin. T is 295 Kelvin. P is 789 torr. We've got to convert that to atmosphere. Alright, so looking at the units, the torr cancels, the atmosphere is canceled, the Kelvin's canceled. That gives us liters per mole. That's what we want. How many moles are there in a liter, or how many liters are there in a mole? So we'll just do this quick calculation, and then we can get the conversion factor. So I'll just do the 0.08206. Times 295 divided by 789 times 760. And it comes out to 23.31. How many sig figs am I allowed? 23.31 liters of gas per mole of gas. And so we're going to use that as a conversion factor here. So the first step in the dimensional analysis, we're going to go from liters of hydrogen, so 2.0 liters of hydrogen gas, to moles using the molar volume, so 23.31 liters per mole. So 1 mole of gas occupies 23.31 liters gas. So this is a hydrogen gas. Liters of gas cancel. That gives us moles of hydrogen gas. So once we're at moles of hydrogen gas, then this is stoichiometry. So in the middle of stoichiometry, we always do a mole-to-mole conversion. So where do we want to go next? To moles of what? We need to go to moles of sodium hydroxide. So we're going to go from moles of hydrogen to moles of sodium hydroxide. Just use the mole ratio. So what is the mole ratio? It's 6 moles of sodium hydroxide for every 3 moles of hydrogen gas. All right, now once we're at moles of sodium hydroxide, sodium hydroxide is a solution. And so they want how many milliliters of sodium hydroxide solution we have. Well, when we have a solution, we can go from moles to liters, and we can go from liters to moles using what? The molarity. The molarity. What is the molarity of this? So we can go from moles of pure, this is pure sodium hydroxide, to liters of sodium hydroxide solution by using the molarity. Now the molarity is what? It's 1.50 molar sodium hydroxide, which means 1.50 moles of sodium hydroxide per liter of sodium hydroxide solution. And so liters of hydrogen gas cancel, moles of hydrogen gas cancel, moles of pure sodium hydroxide, oops, don't cancel. Moles of pure sodium hydroxide don't cancel because I wrote this upside down. This has got to be a liter of sodium hydroxide solution per mole of sodium hydroxide solution. Oh no, not sodium hydroxide solution, per mole of pure sodium hydroxide. And how many moles do I have? I have 1.50. Insert that in there. Now moles of sodium hydroxide cancel, that leaves us with liters. But they don't want liters. What do they want?
Milliliters.
They want milliliters. So I need to tack on one more conversion factor here. That is 1,000 milliliters of anything is a liter of that. So that cancels there. So, we got here, we got to go do the calculation. Doing the calculation is 2 divided by 23.31 times 6 divided by 3 divided by 1.5 times 1,000. 114.4 milliliters of 1.50 molar sodium hydroxide solution is required. So 114 milliliters. They did, which way did they do it? I don't know. They use the ideal gas law here. You can use the ideal gas law to calculate the number of moles. Then we'll do a mole-to-mole conversion here, and the moles to liters of solution conversion here. This top one, they're using the molar volume. They use the molar volume that you're supposed to memorize at STP, and they're converting the molar volume from STP to the correct temperature and pressure, but this is just ridiculous, the way of doing it. I just don't understand why they're doing it that way. It doesn't make any sense to me to do it that way. All right, so this is a standard. This is a more challenging one because not only do you have a gas, but you also have a solution you got to deal with. So it's stoichiometry. Okay, other questions? No other questions? All right. Now we're going to continue with redox reactions. The situation is we really don't need to use the single replacement method. We could really get rid of the single replacement method for redox. We could get rid of single replacement and just replace it with the chart method. But there's an advantage to using the single replacement. The advantage to using the single replacement is that it's quick, it's fast. But you have to weigh that against the disadvantage of using the single replacement. The disadvantage of using the single replacement is you might get it wrong. Well, in what cases does single replacement fail? So let me give you some cases where single replacement fails. Single replacement is easier and faster. Easier is a relative term. It's not easier. It's not easier because you have to memorize the exceptions. Do you want to memorize all the exceptions? So a lot of people say it's easier because they assume it's going to work. And it will work in our book, but it won't work in future courses. This one is slower and more work. But more work, again, that depends on how easy it is for you to memorize the exceptions. So I'm going to give you the choice. You can continue to use single replacement until you're forced to use the chart. Or you could just use the chart for everything. You could use the chart method for everything. And so let's look at some common failures. Failures for single replacement. All right, the first common failure is what we call the oxidizing acids. Oxidizing versus mineral acids. In an oxidizing acid, like nitric acid is called an oxidizing acid versus HCl, which is called a mineral acid. There's a big difference in redox properties between an oxidizing acid and a mineral acid. When we look at an oxidizing acid, we have H plus and nitrate as the inventory. When we look at HCl, we have H plus and Cl minus for the inventory. Now, the difference here is this. H plus is an oxidizing agent. And nitrate in H plus is an oxidizing agent. Over here, H plus is an oxidizing agent, but what is chloride? Chloride is well, if we look at the chart, chloride turns out to be not an oxidizer. It's a reducer. Chlorine is an oxidizer, chloride is a reducer. And so it's a reducer. Now all the trouble with single replacement comes down to the pattern. And we can see the pattern's going to fail in this case because what was the pattern? Yeah. The pattern is A plus BX, is that right? A plus BX yields AX plus B. Now when we break down this reaction, it's going to look like this. A is the reducing agent. B is the oxidizing agent. X is a spectator. Okay, these are the assigned roles. We call it the assigned roles based on single replacement pattern. So the problem here is this. In this case, BX is our oxidizing agent, right? And in fact, BX is our oxidizing agent, but it's B that's doing the oxidizing. X is just along for the reaction. That's fine for HCl. When we look at HCl, we call HCl BX. And what's the oxidizer in HCl? B is the oxidizer, and X is chloride. Chloride's not going to do anything. Is chloride going to oxidize anything? No, it's a reducing agent. It's not going to oxidize anything. But we run into trouble with an oxidizing acid. The reason we run into trouble with an oxidizing acid is this. We have X. X is supposed to be a spectator. Nitrate's supposed to be just watching. Nitrate's not supposed to do anything. But when we compare the strength, which one's a stronger oxidizer? Is nitrate stronger or is H plus stronger? We have two oxidizers. So is nitrate stronger or is H plus stronger? Nitrate's stronger. Nitrate's a stronger oxidizer. However, the single replacement says nitrate cannot react. Nitrate must be a spectator. But do you think if nitrate's stronger than H plus, which one do you think is going to react? Nitrate. So the single replacement fails. The single replacement fails because X is not a spectator. When we're dealing with an oxidizing acid like nitric acid, the anion is a stronger oxidizer than the acid part, the H plus. Does that make sense? And so this is why single replacement failed yesterday when I did this as an example. We took copper metal plus nitric acid, right? And it failed because, you know, single replacement predicts no reaction between copper and nitric acid. But if we were to do this, let's just go ahead and do this. We'll take some copper pennies and then just pour in some nitric acid in this. Let me see. Okay, so pour in some nitric acid, see what happens. Is there a reaction occurring? Yeah, definitely a reaction is occurring. Single replacement predicted no reaction between copper and nitric acid, but that's wrong. There's actually quite a vigorous reaction here. The blue-green is copper 2 ions. This gas, this is the orange gas that's being generated. That comes from the, if we looked at the reaction yesterday, it formed NO gas. The NO gas is oxidized by oxygen in air. NO gas is a CCG, clear colorless gas. It gets oxidized by oxygen in air to NO2. NO2 gas is that red-orange or brown-orange, that kind of the orange gas. It's very poisonous. But you know, they're doing it in a fume hood, so the fumes are being sucked into the hood. Do you see the gas being sucked into the hood? Anyway, this is a component of smog. So sometimes you'll see a red-orange layer, you know, when you're looking out in LA. It's because of oxides of nitrogen. This is why when you go get a car smog, they check for oxides of nitrogen. Oxides of nitrogen produces orange gas, NO2, nitrogen dioxide. All right, so that's a common failure. So whenever we're dealing with an oxidizing acid, you know, we got to watch out. Nitrate's a good oxidizer. Why is nitrate a good oxidizer? Can somebody tell me why nitrate's a good oxidizer? Well, good. What common characteristics do good oxidizers have? Okay, do they give electrons or do they take electrons? Like what's the most common oxidizer? The most common oxidizer is oxygen. In fact, the name oxidizer comes from oxygen. You know, oxygen is the most common oxidizer. It causes metals to corrode, etc. Now, oxygen, does it want to take electrons or does it want to give electrons? Take. One thing that's common for oxidizers is they take electrons. And so why does nitrate want to take electrons? Doesn't it already have an extra electron? It doesn't make sense, does it? And so this is why, you know, of course we can memorize it. Nitrate's a strong oxidizer. We can memorize it. It wants to take electrons. We can memorize it. But if we can understand it more, you know, from a theoretical point, then maybe we could get a better understanding of all oxidizers. And so what in nitrate makes it a strong oxidizer? Those gloves are worthless. Those are food preparation gloves. The nitrile gloves have much better chemical resistance. Well, what about nitric acid? Well, what you want to do is you want to really start to review, because maybe you know don't remember much from the earlier parts. Maybe you do, but you definitely want to start reviewing. That is, hopefully you could just flip back through the notes. But as I said before, if you want, speed counts. I don't like I didn't when I went to UCLA, I didn't like the time test. They're pretty strict. Your pencils or pens had to be down on the table, and then they call out time. When they call out time, then you can pick up your pencil. When they call off time, you have to put your pencil down. If you don't put your pencil down, they knock points off your test, like 10 points off, something like that, if you continue working. And so the thing is, I was always slow. I was always one of the slower people. But I had to change that fast, otherwise I was going to fail miserably. It's not that I didn't know it, I just was slow. And you need faster recall. And so how do you get faster recall? Well, you got to do drills, like sports drills or whatever else. You do mental drills, you get faster recall. You only have 10 weeks. At UCLA they're on quarters, so you have 10 weeks and then 1 week finals. So you gotta have it down by the time you get to the finals. Usually you have one midterm and one final. Well, like we're doing this semester. But anyway, what makes it, well, we look at the oxidation state. What makes it is, what's the oxidation state on nitrogen? Oxidation state on nitrogen is +5. +5 is the max, that's high, that wants electrons. This is why nitrate's a good oxidizer, because of its high oxidation state on nitrogen. The reason the negative charge is not a big deal, but the negative charge comes not from nitrogen, it comes from the oxygens. Each oxygen's O2 minus, they're happy as is. So the extra negative charge just comes from having an extra electron on one of the oxygens, but they aren't going to give it up. And so basically that's it. And so what are the other oxidizing acids that we might be concerned with? Well, there's some big ones. Can you think of a big oxidizing acid that's well, things like this, maybe something like this here. This is what's the name of this called? Permanganate. And if you have this as an H plus with the permanganate, it makes permanganic acid. So this would be an oxidizing acid. What's the oxidation state on manganese here? +7. And then this is lead in the +4, so this is a pretty good oxidizer. It's solid. This one's here not because it's all that common. This is actually very common in batteries. So automobile batteries use this as the oxidizer. It's a solid oxidizer. So we got chlorine. And chlorine 0, ozone 0, fluorine 0. But all those want electrons. All those are kind of small. So dichromate. Chromium's in the +6. Manganese 4 oxide, manganese is in the +4, oxygens in the 0, iodate, this would be iodic acid, iodate is in the +6, yeah, or +5, bromine's in the 0, nitrates in the +1. So usually high oxidation state. So one of the more nasty ones that aren't on this chart would be like this. Would you classify this as a mineral acid, or would you classify this as an oxidizing acid, HClO4? A mineral acid? Mineral acid, the anion is just going to be a spectator in redox reactions. How about this anion? It's an oxidizing acid. What's the oxidation state of chlorine here? +7, good. +7 is very high. This is going to be a very dangerous acid. It's a strong acid, but worse than, or potentially more dangerous than that, it's a powerful oxidizer. So whenever we're dealing with an oxidizing acid, single replacement is going to fail. It's going to fail. And so best, if we're dealing with oxidizing acid, we have to do it like we did yesterday. We have to use the chart method. Sometimes our chart's not comprehensive enough, but like perchlorate's not on here, but we can find other charts where it's there, or we can figure out do based on that. All the failures are based on misassigning the roles. There's misassigned roles here. The next failure is going to be with the halogens. I'd label that 1A, B. The halogens are going to fail. Halogens would be like chlorine, bromine, etc. So for example here, chlorine plus potassium bromide yields what? You know, this looks like a single replacement, doesn't it? But it's not, because what do you know? Oh, my battery's going to die.